Hi, my name is Karol, and with Maciej we would like to share our experience with building this large-scale e-commerce recommender system. And the system we are about to present recommends product by finding nearest neighbors in latent space. And to do this, we need a high-quality product embeddings, hence the title of this presentation. Before going into the details of the system, let me briefly introduce our company and basic taxonomy of recommender systems. So Allegro is an online marketplace. It's not an online store, so it does not sell products, but provide a platform for third-party sellers to sell their products. And there are almost 400,000 of those sellers, and this makes Allegro the largest e-commerce in Poland, and in fact, it's also the sixth largest in Europe, in European Union in terms of turnover, but it operates only in Poland. And just to give you some idea, there are numbers. To give you some idea of the scale, there are some numbers. So we have 20 million accounts and over 100 million offers or items. The number of unique products is smaller because there are some duplicates. Some products are being sold by multiple sellers. Some products are being sold under different names. And recommender systems, we distinguish two main categories, collaborative filtering and content-based. And this term collaborative filtering has two meanings, one narrow one and one broad or generic one. And in a narrow one, collaborative filtering is just an algorithm to predict ratings users give to items. And in this broader one, it's a family of algorithms that predict future user behaviors based on past user behaviors. And further on in this presentation, we will use collaborative filtering in this broader sense. And we define two subtypes of collaborative filtering, namely item to item. So when you recommend a similar products to a given product, and user to item when you recommend products to a user profile. And we can build those systems either based on explicit or implicit feedback. In case of e-commerce, it's much easier to build it based on implicit feedback because this kind of feedback is much easier to collect. And the second type is content-based systems. Those systems basically recommend products by finding similar products in the sense of content. And by content, we mean either title or description or parameters or images of products. And the question is which of those two is better, and in general collaborative filtering at scale always win. I mean, we tested it multiple times in A/B test, and at scale always collaborative filtering wins, but sometimes we explicitly prefer content-based. For example, in fashion we want to recommend similar dresses or similar shoes based on images. And sometimes we cannot use collaborative filtering because to do this we need a number of past activities associated with products. And for new products we do not have those activities. And also for old products, I mean for products that exist in our platform for a longer time, we sometimes do not have enough number of activities because there is this relatively small number of products that are frequently visited and purchased and a long tail of products that are rarely visited. So we cannot recommend products for this long tail. So the common strategy is to use collaborative filtering whenever it's possible and fall back on content-based when it's not possible to use collaborative filtering. And the question is, can we do better? And yes, later on we will describe a strategy how to recommend using those crowd-based methods or behavioral methods for those freshly added products as well. Okay, and recommendations are important for e-commerce and for Allegro as well. They generate around 10% of total sales. So, yeah. And we have around 33 placements or carousels or shelves, the same name, different names for the same thing. And those shelves or carousels are available on desktop and mobile applications and in email campaigns as well. And you can see just shares of those placements and shares by total sale. And the important takeaway from this slide is that 3 out of 4 most important shelves or carousels are located on the product page. Therefore, those item-to-item recommendations are of high importance for us. They are more important for us than user-to-item. User-to-item is only or mainly presented on the main page, but majority of users end up in our platform. They are directly redirected from Google search. So, yeah. And you can just have a look at example product page. There are 2 main carousels. One recommends product for the same seller, and one for all the sellers in the platform. And here is a fragment of the main page. And as I said, on the main page, we provide user-to-item recommendations. They are not as profitable, but still we want to inspire users who come to our platform without any specific purpose. And we divide those shelves into most frequently visited, categories the user visited in the past.
Okay, hi everyone. So now let's take a look at our solution. So our design consists of 4 main parts. The first one is the ETL module, which is responsible for preparing the training data set. The second one is the embeddings model, the representation learning model, which actually gives us the embeddings. The third one is the nearest neighbor search module, which actually gives us the recommendations based on the embeddings. And the fourth one is the real-time serving module. So let me begin with the ETL module. Well, different scenarios, different business scenarios placements require different recommendation logic. Hence, we need to extract different data. And in case of collaborative filtering, we extract either sequences of visited product IDs from user sessions extracted from clickstream data, or we rely on transactional data like purchases and cards to obtain recommendations on a complementary basis. In case of content-based recommenders, which are often our fallback recommenders, we extract product titles, category paths, and product images from our product database. In order to do this, we implemented several SKIO jobs. SKIO is a Scala wrapper around Apache Beam Java, not Python API, and it gives us really concise syntax, strong typing, and good testability, and we highly recommend this tool. This was the first part, the data preparation part. Now let's take a look at one of the 2 pillars of our solution, namely the embeddings module. The key idea of our system is to find latent space representation for products available on our platform, or in plain English, to convert products to real valued vectors, multidimensional vectors. The dimensions of this space do not have any human interpretation. What we care about most is that they should preserve item similarity. So similar products should have similar embeddings. And by similar embeddings, we usually mean low cosine distance. So as you can see, an iPhone has its representation. An iPad, which is something quite similar, has a quite similar embedding, while a pair of sneakers has its vector directed in a totally different direction. This is the theory. And how can we obtain such vectors, such representations? Well, in order to do it, we use an algorithm which originates from natural language processing. It's called Word2Vec, presented in 2013. And it comes in 2 flavors. The first, called Continuous Bag of Words, or CBOW, tries to learn how to predict a central word given surrounding or context words. The second flavor, called Skipgram, is a dual version. It tries to predict the context words given a central word. And we actually use this second version. Okay, so we know how to obtain word embeddings, but how do we obtain product embeddings? The transition and the answer is surprisingly simple. It's called Prod2Vec. And the only thing we have to do is to actually change the vocabulary. So we use as sentences, we use user sessions, and as words, we use product IDs. The rest stays the same. This way, using skipgram, we can predict the surrounding products given a central product, for instance, the one you're currently watching. So the true aim of our model is to learn to predict surrounding products given the central product. There's nothing about recommendations in this, at this stage. We rely on system-wide implicit feedback. So we don't restrict ourselves to data generated by recommender system in the past. We rely on the entire click stream. And by doing so, we reduce the bias from past recommendations, and we have much more training data. It is important to notice that the product embeddings here are in fact side effects of the training process of the word-to-vec model. It is also important to say that word2vec actually implicitly decomposes the item-to-item interaction matrix, and it does it in a way that has a relatively low memory footprint, and it's quite resilient to data sparsity, which is a huge problem in our setting, and we will discuss it later. So suppose we have some a embedding, a mapping, a set of vectors. So is the good embedding? Is it better than the random set of vectors? The one desired property of embedding is that it preserves item similarity. So similar items should have similar vectors. And the graph you see behind me is actually shows a sample of products on Allegro colored by their top-level category. And you can clearly see the separation between these categories. Another desired property of embeddings is that it should preserve relations between items. And now for a second, let's pretend that Allegro sells only men's shoes, women's shoes, men's clothes, and women's clothes. And these items have at least two orthogonal aspects, the gender of the product and the type of the product. Is it a shoe or is it clothes? And this graph shows these subset of products projected onto 2D, and you can clearly see these two aspects along the vertical and the horizontal axis. So finding such relations gave us some confidence that our vectors are something valuable. So as I previously mentioned, different placements require different recommender logic. And on product pages, in general, we want to show similar products. In order to obtain this effect, we train on sequences of product page views, while in cart and some post-buy emails, we want to show complementary products. And in order to achieve this, we train on transactional data. So the model stays the same. What changes is the input. All I've just said refers to collaborative filtering recommenders, and as Karol mentioned, there are sometimes we cannot use these methods. So we fall back on content-based recommenders, and basically we use two types of them, one based on text and one based on product images. So in the case of text, we learn the representations of individual words present in product titles using fast text, and then we combine these representations in order to get the vector of the product title. In case of images, we use a deep neural network, Inception v3, pre-trained on ImageNet dataset, and then fine-tuned by our colleagues from other team on Allegro products.
Okay, once we have high-quality product embeddings, we need to turn them into recommendations. And to do this, we need a nearest neighbors search module or component. This component is a second pillar of our system. The naive approach would be to do this would be to calculate distances between a query product and or remaining products, then sort all those products and select a few nearest neighbors. But this is very expensive. This would take too much time. It would be infeasible in practice. So we need some approximation. And of course, approximation introduces some errors. Approximation is not as good as this exact method or brute search brute force search approach. But some type of errors is acceptable for us. What we care is the high precision of results. We can compromise on recall. So there is this saying that what the eye doesn't see, the heart doesn't grieve over. So we basically follow this principle, and we focus to. We try to have not to have false positives, but if we have some false negatives, there is no problem for us, because what we care is to have relevant recommendations for a given product. If some relevant products are not presented on this shelf or carousel, the user does not know about it. So, there are many approximate nearest neighbor search algorithms. Most of them can retrieve those neighbors in almost constant time, very quickly. And probably the most popular is random hyperplane projection, also known as locality-sensitive hashing. And the idea is just to split a search space with random hyperplanes to form hypercubes. And then the most similar product, or in general, most similar vectors in the original vector space will end up in the same hypercube. So in order to retrieve those similar vectors, we just need to browse through this hypercube, maybe a few nearby hypercubes. And this algorithm is implemented by popular library Spotify Annoy. And at the beginning, we were using this library, but then we switched to Facebook FICE. FICE is a similar library, but it has a few advantages. For example, it is GPU accelerated. And a few words how FICE works. So basically, it implements a two-stage searching strategy. So at the beginning, we need to train our index. And during this training, all the vectors are clustered into relatively small number of partitions, also known as Voronoi cells. And each of those partitions is represented by a centroid, which is just a mean of vectors within this cluster. And at search time, what we do, we just retrieve the most similar Voronoi cells. And this way we significantly narrow search space. And then in this narrowed search space, we can afford exact search or brute force search, because the search space is much smaller now. We could introduce even further speed up and reduce the memory requirements even more by using some more advanced quantization techniques. FICE implements those more sophisticated quantization techniques, but in our case, it was just enough to use this two-stage strategy without more advanced quantization techniques. But there's a paper which describes those ideas. And a few more details how this nearest neighbor search module works or is implemented. So basically for collaborative filtering recommendations, we built just one big FICE index because there is relatively, we can build this index, and for content-based, it was too big. To put all 100 million embeddings into one FICE index, we could not find a big enough machine in GCP. So we decided to split and build a separate FICE indices for every top-level category. We have around 20 of those top-level product categories on our platform. And also one important thing is that we do not want those neighbors to be too similar to original, to the query product, because often we end up with almost the same products. We want some diversity in the recommendation is desired. So we introduce some minimal delta or minimal distance between a query product and remaining products, and also between pairs of products at the neighbor list. And of course, to select this delta can be treated as a hyperparameter, so it's not easy to select good delta, good minimal distance. It have to be done in some experimental way. Also, one important thing is that we eagerly pre-compute all recommendations. So for all the products on our platform, we eagerly pre-compute daily recommendations. I mean, we could do this. We could retrieve those neighbors in online fashion, but in most cases, it's enough to do this offline and then serve just pre-computed recommendations. I will tell about this later on a little bit. Okay, those 3 modules described till now run in public cloud, and we need some orchestration tool to run those, to schedule those tasks. And we use Spotify Luigi. It's a similar library as Apache Airflow. There are 2 main concepts: the concept of task and concept of target. And every task has multiple inputs and 1 output. And if some input is missing, then the scheduler is scheduling tasks that produce those inputs. And this way, the whole graph of dependencies is built. And Luigi is easily extendable. We implemented a few custom tasks and targets, for example, to submit a cloud machine learning task or a Google Dataflow task. Okay, and serving. As I said, at serving time, we just retrieve pre-computed recommendations from read-oriented key value store. In our case, it's Cassandra, so we store a lot of those source to target relations. But of course, before returning recommendations to user, we need to enrich those set of IDs with some metadata, descriptions, images, just to form a ready to be presented set of recommendations. And also we need to filter out some elements, because if recommendations are built daily, then after those recommendations are pre-computed, some product can be no longer available at our platform. So we need to check before returning recommendations to a user, whether the products are still available. Okay, re-ranking is very important in information retrieval. Most of the search engines apply some sort of learning to rank re-ranking on top of result returned from, let's say, inverted list search engines. And in case of Allegro, learning to rank improves results by 10%. So we wanted to apply the same idea to recommendations. And in fact, in recent years, there are many papers that prove that it's good idea to apply learning to rank re-ranking on top of some recommendation system. And we experiment with this, but it's not, I mean, not every placement has already this strategy applied in our company, but we experiment with this learning to rank on top of nearest neighbors search recommendation system. Okay, at the beginning I told you that, and also Maciej mentioned that we serve collaborative filtering whenever we can, and we fall back on content base when there is not enough past events associated with products. And we wanted to do better, basically to be able to recommend those behavioral recommendations for every product, even for products that do not have past activities. So in order to do this, we introduced a concept of proxy product, let's say. So for those products that do not have activities associated with them, do not have past histories, we retrieve nearest neighbor in content space, but narrowed to only popular items. So this way we retrieve proxy product, proxy neighbor, and this neighbor already has activities, so we can serve collaborative filtering recommendations even for products that are recently added, freshly added to the platform. On the bottom of this slide, you can see a diagram that describes this idea. Basically, one additional auxiliary files index is needed to do this. Okay, the second approach we also experimented with that tries to solve the same problem is metaprod2vec. It was this idea described in this paper. So basically, instead of training skipgram on just product IDs, as Maciej described earlier, we enrich those sessions with metadata identifiers. So we can do this only for categorical metadata, like, let's say, color. And of course, we need to extend window size because those sessions are extended, so we need to proportionally extend the size of the window. And as a consequence, there are two consequences of this idea. The first, product embeddings have better quality now, because, for example, products with the same metadata, let's say red products, are somehow are drawn together in the vector space. The second benefit is that we obtain metadata embeddings, and those embeddings are embedded in the same vector space. And we can, for freshly added products, we can take their embeddings, find or look up, take metadata of those freshly added products, look up embeddings of those metadata, and find nearest neighbors, and find products that are near those metadata. I hope it's maybe it's not clear. You can read this paper. It's clearly this idea is described in this paper, and yeah, we experimented with this idea as well. But the first idea, the first strategy I described on the previous slide is our main, let's say, hybrid recommendation strategy. Okay.
Okay. So. What about the user? So far, we've talked only about item-to-item recommendations, which is reasonable given the share of product pages in Allegro traffic. But still, we want to be able to serve recommendations directly to the user. These recommendations differ from item-to-item recommendations by at least in at least two ways. The first one is that there is no explicit product context. We have to rely on some sort of user profile. And the second one is that it has slightly different aim. The aim is to inspire users to make new purchases, not to shorten the so-called path to purchase, as it is in the case of item-to-item recommendations. Also, these user-to-item recommendations are applicable to email campaigns. So how can we obtain such user-to-item recommendations given our setup and our setting and our item vectors? So the first, the most ambitious, the cleanest approach is to simply learn the latent representation of user the same way we learn the latent representation of the items. This would mean that we have to somehow decompose a hypothetical user-to-item interaction matrix. But in our setting, we believe it is impossible to do because we cannot do it in real time. And this is the whole trick. We want these recommendations to update in real time as the user browses different items and he or she returns to the main page. We would like to see recommendations relevant to the latest query, latest search, or recently visited items, and we cannot recompute the entire. We cannot perform this decomposition in the real time. But still, it's good and applicable to email campaigns. Okay, so this is the first approach. The second one is the one we're currently experimenting with, is to obtain the user representation as an aggregation of representations of products. Yeah, like a sum or an average. This in turn requires an online nearest neighbor search because the query vectors will be unpredictable. We cannot predict every possible browsing history. So this requires an online search, and the challenge here is to keep the latency as low as possible because we no longer can pre-compute everything. We have to actually find the nearest neighbors real time. The third option, the simplest one, which actually runs in production now, is to have no user representation at all. Namely, we simply interleave item-to-item representations of the visited items. It's easy to implement, fast to serve at runtime. The complexity here is the problem here is how to interleave these recommendations originating from different visited items. Now I'd like to share a couple of considerations and conclusions we learned during development of this system. So first one is hyperparameter tuning. Whenever you have a machine learning model, you probably have to tune some hyperparameters, and the tuning does, in fact, improve the quality of your result. In our case, of our recommendations. We were lucky enough that there is some literature on this topic. First of all, there is this great paper called Hyperparameters Matter, and it describes how to tune the parameters of word2vec exactly in the context of recommendations. We followed this paper. We managed to recreate some of its results, and it indeed significantly improved the quality of our recommendations. We carried out this hyperparameter tuning process the following way. We simply held out some number of train sessions. We trained the model on the remaining part, and then we tried to predict the last item given the penultimate one from these holdout sessions. And we optimized the MRR at 25, which is the length of the shelf, aka carousel in our system. Initially, we performed this procedure in Google Cloud ML Engine, which is a very convenient tool, but it turned out to be quite expensive. The next trial runs, we run them on static instances using HyperOpt library, and it gives us similar results, but it turned out to be much, much cheaper. So I recommend this approach. Okay, so other part is are some data considerations and challenges. They are highly specific to our scenario. Namely, Allegro is an online marketplace, not an online store. So there are many sellers, and the same product can be offered by multiple sellers. And despite a huge effort to match offers to products, most of the offers don't have a product ID. So we don't know that two separate offers actually refer to the same product, say an iPhone. And this causes a lot of problems. The biggest problem is the decrease in the quality of recommendations, because if we recommend on a per offer basis, we get some noise because accidental co-occurrences become relatively strong in the context of a particular seller. Moreover, the data grows big. The dictionary of IDs for which we compute the representations is very large, and it's simply problematic. So what we try to do is we try to match the unmatched offers into some pseudo products or groups of offers. We do it by title or by category or by some set of attributes. In general, we want less objects and a denser interaction matrix. Because we've proven that product-based recommendations give us much better results by simply changing the way of the type of objects on which we operate with the same algorithm. We managed to increase the click-through rate by almost half and the revenue by almost a third. No algorithm change, just a switch from offers to products. But in this scenario, there is a new problem, namely the choice of the representant of a given product. Namely, we have to choose the best offer for product from our similarity model. And we can do it by choosing the cheapest one, include the free delivery, and so on. In general, we plan to solve this issue using the re-ranking algorithms.
Okay, so just one slide. Yeah, just last slide. So just the key takeaways. So we introduced, we described a relatively simple yet production-ready and large-scale e-commerce recommender system, and the system is based on this framework with clearly defined modules, and it can run either in public cloud or on-premise, and we use it for both collaborative filtering and content-based recommendations. And yeah, maybe that's all. Just one. Yeah. So thank you very much, and if you have any questions, feel free to ask.
Thanks for a great talk. You mentioned briefly bias when representation learning in terms of the user sessions. Presumably, though, still people are clicking from one product to the next using the sort of similar items that you're already showing. Presumably, it's really hard to completely eliminate that bias. Do you have any other sort of strategies to deal with that? Do you find it's a problem?
Yes, the main trick to mitigate this problem is not to rely on only on interactions originating from past recommender system, these parts rendered by recommender system, but on the entire traffic, which includes some static creations, the search engine, and so on and so forth. So I'm sure that the bias is still there, but it's not the bias originating from the recommender system. Probably some sort of a mixture of bias from the search engine and other aspects.
Okay, thank you. Some other questions?
Hello, thank you very much for the talk. Have you tried using any of the latest Jensen features like Ponker embeddings or word movers distance? And did you find them applicable in this industry?
No, we didn't.
But we're happy to learn about these features later.
We have one more question, I think. We have a few minutes, but it's really sorry about that.
Yeah, I have a whole bunch of questions, so I'm going to come and see you guys later. But I guess one that I'll ask now is, you said that when you were doing the user item embeddings, you guys had 3 different options, and you chose one which was no user representation, but you interleave sort of item representations. I just wasn't entirely sure what you were interleaving. I was hoping you could expand on what it was that, in terms of that, basically.
Anyway, the trick is simple. We have an internal database of things you have browsed, and we have item-to-item recommendations for those things. So the strategy is to take your last visited item and mix it with recommendations from the penultimate and so on and so forth. And the question here is, how do you interleave these items? Basically, we take the strategy now is very simple. We just take the first recommendation from the last item, the first recommendation from the penultimate one, and so on and so forth. And then we take the second recommendation from the first item, and so on and so forth. And it performs reasonably well.
Thank you to the speakers, and please an applause. And during